Well, welcome back.
Hjorth.
And the aim this week is to discuss the backpropagation algorithm together with the auto-differentiation algorithm. And then when we are done with that, we are going to move over to study the structure of a program for setting up a neural network. And then we are going to bring in everything which we have done. We are going to bring in the gradient descent methods, which you've been working on in project number 1. We're going to look at how to include stochastic gradient descent, the various learning rate adapters. We are going to bake in different cost functions, etc., etc., etc. Just a quick reminder, as usual, after every lecture, you will typically find the slides, or the slides actually have access to them before, but then there's a video of the lecture and also the handwritten notes. So last week we looked at the backpropagation algorithm and we derived it. And then we tried to link this with automatic differentiation. So this is part number 2 here. And then we are going also to dive into the code for setting up a neural network and which are the basic ingredients which we need. And the video of the lecture is going to come later, and the same with the lecture notes. So what I'm going to do now, I wanted to just quickly remind you of what we did last week. And we are going to set up some of the equations, and then we are going to look at an example of the backpropagation algorithm and the automatic differentiation and how we can link the two. So one of the things I wanted to remind you of, and please feel free to interrupt me if something is wrong or you don't see the screen, or just if you have questions. So let's look at a feed-forward neural network, and we use the acronym FFFNN. And the basic setup of a network and was given by a input layer, which we just indicate with this vector X or a matrix X. So this is the input layer. And then we have a set of weights which connect the input layer with the first hidden layer. So this will be our first hidden layer. And what we did then in this hidden layer was that we had the weights and the biases. So in here we had the unknown parameters, the weights of this specific matrix in terms of, we would normally write it in terms of a matrix. And then we had the bias, and we are writing this out as matrices and vectors. So this is hidden 1. Now this produced an output, which we labeled with an A1. And this was modulated by an activation function, which we call just sigma 1. And that had as input a Z1, where this Z1 is simply given by the matrix W1 multiplied with the input plus this bias B1. So if X is a vector and W is a matrix, we get a vector plus a vector, which has the length of the number of nodes which we have in the first hidden layer. So this produces an output which we label with A1, and then this feeds into the next hidden layer. So we got a new set of weights, which we could simply call W2, V2. We have a new input here to the given nodes, which we simply label by a C2, and that produced an output, an A2 here, which was modulated by this activation function. So the activation functions can change from layer to layer. And this would move on all the way till the final layer, or the next to final layer. So we would have now an input from layer L-1, and this was modulated by an activation function, L-1, which took as an input set Z of L-1. And this was fed into the output layer, which is the last layer here. So this is the output. And we label that one with a superscript with uppercase L. So we have an input Z of L. We have the weights WL. We have the biases WL. And then this produced also an output, this A of L, which we labeled as Y. So that's our final output here. And this is also modulated by an activation function. So in case we just have one output, this could be a binary case where we have a yes-no case. We could simply use the sigmoid function. If we had a multi-class case, like this handwritten numbers, you would have 10 handwritten numbers. You could use this softmax function. If you're dealing with a regression case where you want to fit specific function values, then it's normal to not have a activation function in the output layer, but simply just let the network output a final value for y. So this takes as input this C of L, and this value is then sent into the cost function, which we denoted by a C, or loss function, and this receives as input the targets here. So that means that this specific output y, when we write it in a vectorized form, this is given by this A of L, which is a function of all these variables and the input parameters. I'm going to come back to what these parameters are. So these theta, is a common denominator for all the weights and the biases, B1, W2, B2, etc., up to the final weights and biases, B of L here. So these are all the parameters which we want to optimize. And this function here is now given by obviously this activation function, sigma of L, with an input Z of L. And this quantity can then be rewritten if we look at this quantity sigma L of ZL. That contains the input from the previous layers. So that is given by sigma, which again receives as input the output from the layer L-1, which in turn receives the output from layer L-2, etc., till the final first layer, sigma 1. And we have a Z1 here, and then I'm just going to put dots. And if you look back at the drawing here, these parameters are then defined by the first hidden layer. We start with the first hidden layer. Keep in mind that X, the input, is fixed. So we don't change the input. We can have so-called generative networks where we do change the input, but that's not something which is normal for a standard neural network calculation. Your targets and the inputs, they are fixed. And then you let the network produce this value y, which we denoted by this A of L in our machinery last time. And so this sigma of L is actually a chain of operations, and this is actually what brings the brings up the non-linearity in the model here, which we could not achieve if we didn't have a hidden layer. Then the cost function, which now depends on all these parameters, is something which we, in case we are dealing with a regression problem, this is simply given by the norm 2 of the target minus this quantity AL, which depends on theta and the input X. And we write, so this could be the one typical example of a cost function. So this is the mean squared error. And I've skipped the term 1/2 or 1 over n here. So the mean squared error in regression. So it's a typical equation which we would use as a cost function if we want to fit our data to some specific function here. So the optimization problem then means that what we have to do is simply to calculate the derivatives and find the gradients. So we need a backpropagation algorithm to find the gradients. And if you now look at the backpropagation stage, what we are doing then is that we start with a function at the end. We start with a cost function, and we want to have that as a function of the parameters from all the preceding layers. So we would typically start then with dc and d theta of L, and we want that one to be equal to 0. So that's a typical optimization requirement which we would set up. Now, we can then calculate the gradients because we're going to update all the parameters. So if we now look at the previous layer, so we would now have a dc d theta of L-1, and we can then use a chain rule to rewrite this in terms of the parameters which we have. So we would have a parameter A of L here, of d A of L, and d theta of L minus 1. And then we can move on. We can rewrite this as a dc d theta of L minus 2. And you start to see a pattern now, which we are going to link up with the automatic differentiation algorithm, where we can link it either to the forward mode or the reverse mode, which we discussed last time. So this would be given. So these were the basic equations which we started with last time. And this is now given by a dA of L, dA of L minus 1. So just a repeated application of the chain rule. And then we end up with a d theta of L minus 2. And we could continue like this. And the general expression then, when we look at a specific derivative for the unknown parameters theta, which we want to update for a specific layer L, lowercase l, this would now be given by dc dA of L, and then I would have a dA L minus 1, dA L minus 1, dA L minus 2. So these are the outputs from the layers. And this goes all the way up to the final layer L, which we're looking at. So we would have a d of L plus 1, and then the derivative with respect to d of theta L. This is, in essence, the discussion of the backpropagation algorithm, which we use to set up these parameters. And then what we would have would be that this theta of L as a function of iteration k plus 1 is given by the previous value of k, this value a. We would have a learning rate eta, which would depend on this parameter here. And then we would have the dc d theta of L. And this is then evaluated at theta L equal theta L at iteration k. And keep in mind now that these expressions here contain both the biases and the weights in the training of the data in order to optimize the cost function. So what we want is a cost function which is put equal to 0 when we is the gradient of the cost function. So this is what we are going to train against. So we want this gradient to vanish, but we don't want the other gradients to vanish at the end. So we want actually to have gradients which do not vanish. And in order to do that, there are many, many different recipes, which we will come back to a little bit later. So this is essentially the basic setup of the automatic differentiation algorithm, which we are going to look at now. So this is a backpropagation, but let's go back to what we did last week with automatic differentiation and try to link the two here. So one of the cases which we looked at last time, and one of the reasons why we want to use automatic differentiation is, one, if we take a standard finite difference derivation, what happens then is that we will often have something which can be prone to round off errors and then lead to loss of numerical precision, because we are taking the difference between two adjacent values, which then depend on a step size which we have defined. So we can obviously make this step size smaller and smaller, but then we can easily run into a region of loss of numerical precision, which then lead, or round off errors, which then lead to loss of numerical precision. Another possibility is obviously to calculate these derivatives using symbolic packages like Mathematica or SymPy and so on. The problem often with many of these packages is that the results for the derivatives, which are given in terms of analytical expressions, which we have to code, they can often be less useful from a computational point of view. So let's now look at a function here of which we want to calculate the derivative. So suppose we have f of x, and this is given by x squared plus the exponential, and this is the function which we started to look at last time. If we now do the counting of floating point operations, and we are going to make an assumption now that every floating point operation takes an equal amount of time. So the number of operations needed to calculate an addition is now assumed to be the same as the number of floating point operations which are needed to multiply two quantities. This is not correct, but we are simply making this expansion. Similarly, when we calculate an exponential of an argument, we are assuming now that this counts as one floating point operations. So if you look at the expression which we have here, and we code this in a brute force way, so that means that we calculate x times x. So that is obviously one floating point operation, one flop. Then we have an addition. So we have x squared is equal, plus, rather we calculate the x squared again as an input into the exponential. We could eventually save it because that's the smarter way of doing that. So if we now look at the expression here, we could also think of the exponential here. So if we look at that quantity, so we have the exponential of x squared. If we do this in a very brute force way, we would now think of this as exponential of x times x. So that is going to give us two floating point operations. If we don't think, here it's natural to actually calculate x squared and store that as a variable and not feed that into the exponential. But let's now just treat this as a very stupid way of setting up things. And in addition here, we have an addition. So that is one flop. So we calculate this quantity. So we have 1, 2, 1, 3, 4 flops. And then we have the square root of this expression of that one. So we count that one as one flop. So in total then, we have 5 floating point operations if we don't think. If we do some thinking, we can reduce this to 4 in a brute force way. Now let's now take a look at the derivative. So we calculate now d of x. And if I were to use a package like Mathematica, this would give me a derivative which looks like x plus 1 times the exponential squared. And then I have a denominator, and then I have the square root here. So if we now just stay with the same type of operations which we put up, what we would have 5 floating point operations for the denominator. And if you look at the numerator, we have now x times x and the exponential, so that's 2 floating point operations. We have an addition, 1 plus the exponential, so that gives us 3 floating point operations. And then I have a multiplication with x, and then I have a division. So this results, when you do the algebra, if we don't think, into 10 floating point operations. Now, in reality, we do actually have more floating point operations because we're actually going to calculate the exponentials, and we're also going to do multiplications, and we're going to do square roots. So these require more floating point operation than just one addition or one subtraction. Now, let's now look at the way we define the derivatives of this specific function. So this is just the basic recipe behind automatic derivation. So what we would do now when we do automatic derivation, the basic steps. So what we did now was just a brute force calculation in case we could calculate the derivative analytically. So let's put up automatic differentiation. And in that case, what I would do now is to define a new function, which I call a, which is x squared. I will define a new function, which I call b, which is e times x of a, ex of a. Then I define a new function c, which is a plus b. And then I have a final function, which is the square root of c, which is the same as our function f of x. Now, when I'm now calculating the derivative, what I want is d of f with respect to x, obviously. This is the quantity which we are going to need at the end. But what we can do now is to perform some intermediate steps here. So one of the intermediate steps is to calculate dA of dx, which is pretty straightforward. This gives us 2x. Then my next step is to set up dB of d of x. And this is the same as dB of dA, and then dA dx. I guess nobody disagrees with that. So then we have a pretty easy expression. So that simply gives us then 2x times the exponential of a, which is the same as x squared, which is what we will expect here. Then, if I look at dc, so let's now look at dc of d of x here. This is something which we can rewrite as a dc dA dx. We have to be a little bit careful now because c depends on both a and b. So I have to take the derivative with respect to a. So that means I have that quantity. And then I have the next quantity, which is dc dB. And then I have a dB dx. And I can rewrite this in terms of the following. So I have my dc dA dx plus this dc dB dB dA, and then I have dA dx here. So I know also that this dc with respect to dA is the same as dB with respect to dA. The next step I need is then d of d with respect to c, and that's pretty easy to set up. So that's equal to 1 over 2 over square root of c. So if we look back at the definition of d, if I take the derivative of that one with respect to that, and if I now want to do the derivative of dd with respect to x, which is the same as our function df of d of x, this is obviously the same as d of d, dc, multiplied with dc of d of x. And we know that this one is nothing but 1 over 2 over square root of c, and then I have dc of d of x, which I then can pick up again. This d of dc of x is the one which you can pick up here. So by this specific way, we can actually set up the different derivatives. And this would be typically what we would do now in a so-called forward mode. So we start with the first derivatives. So we will start calculating dA dx. We move on and calculate dB dx. We calculate dC dx. And then we do this one. And then finally, we have the final expression here. So as we discussed last time, this would be the so-called forward mode. And I leave it to you to count the number of floating point operations here when we calculate the derivatives. So what we're going to first do is actually set this up in a graphical way. So what we're going to do now is just to feed this in to a function. So we have a here, and that is given by x squared. So that's a specific function which is fed in here. Then we have a small detour, and we calculate the exponential in order to get this quantity b, which is given by the exponential of a. And this is now brought back here again, where we add this other quantity, which is a. So in here, we feed in a to b, but we feed it also in here, and that produces c. So c is a plus b. And this continues now and produces d, which is given by the square root of c. So that's the new operation. And that gives us finally f here. So one thing we can do now is to compute df dx by going backward. So compute df dx in backward mode, or reverse mode as it's normally called. Backward / reverse mode. So what we do then is the following. So we are going to calculate the derivative of f with respect to c, because we know that df dd is just equal to 1. So the first thing we need now, since c is an argument to f, we need now to have df of dc. And this is obviously something which we have given as df dd, and then d of D with DC. And we know that since df dd is equal to 1, this is nothing but 1 over 2 over the square root of c. The next thing we need now is df with respect to, df with respect to dB, which is the same as df dc of dB. That's the next quantity which we need. And in this specific case, we know that dc with respect to b, if you look at that one, if you now remember that c is equal to a plus b, that means clearly that dc dB is just equal to 1. So we can put this one equal to 1 over 2 of square root of c immediately. The next thing we need is the previous argument, which is df of dA, which is nothing but df of dB dA, but then we need to have the function c as well. So we have df dc times dc of d of a here. So this is just setting up the derivatives using the chain rule. And we know then that when we plug things in, we have the expression for this quantity. We also have calculated this quantity here. We have this quantity, which again is just equal to this quantity. And then we also know the value of dc with respect to dA, which is just 1, since we have that one here. So we can actually plug this in. And what we end up with then is 1 over 2 over square root of c here. And then we have 1 plus, and then we have the exponential of a. And then the final expression which we need here is a df of d of x. And that's going to be the same as df of d of a of dA of dx. And we know the value of dA dx, that is simply 2 times x. And then we multiply with the previous expression. And what we get then is obviously the same result as before, 1 plus the exponential of x squared divided by the square root of x squared plus the exponential of x squared, which we now can rewrite in a smarter way using these definitions which we had. So we had a df dx, which is now equal to x of 1 plus this quantity b. And then we have a plus b. This is actually the function which we need to evaluate. And when we do automatic differentiation in this backward or reverse mode, this is the final expression which we end up with, because we are simply setting up all these derivatives at the different points or different function points. The specific points which we have here, we're just going backward and calculating the derivatives. Now, if you now want to do the floating point operations, if you think of the numerator, what you would have now is that the quantity b is something we have pre-calculated. We pre-calculated b when we calculated f. So b is calculated. So we won't calculate it again because we have it already in the calculation of f. Is calculated in f. So this is a pre-calculated quantity. So that means that if you look at the numerator, there is a multiplication with x, and then there is an addition of 1 plus b, and b is a pre-calculated number when we wanted to evaluate the function. And that means that here we have 2 floating point operations. If we then look at the denominator, in the denominator, we have already calculated a plus b. So that is a, we have a, and we have b. So these are pre-calculated when we also evaluated f. And then that means that if we take the denominator by itself, denominator, then we have one addition, a plus b plus a square root. So that's 2 flops. And then finally, we need to add the division. So that gives us in total 5 floating point operations. Now, if you go back to the original equation which we had, if we were to use a symbolic package like Mathematica, Mathematica would give us this expression which you see up here, this one. And if we calculate that one without thinking, so Mathematica can even translate this into a C++ or Python code for us. But then what the code would do is simply to code these specific equations. And if we do this in a brute force way, that would actually require 10 floating point operations. On the other hand, if I use this formula based on the chain rule and calculate the derivatives, I am down to 5 floating point operations, as you can see here. Assuming then that I obviously have pre-calculated these quantities A and B when I calculate F here. And just to remind you, F of X, which we need when we are performing these calculations, F of X is given by X squared plus EXP X squared, which again is the same as A plus B, and then the square root of. So you see now that the denominator, we could even reduce that one by simply using a pre-calculated value. So we could reduce the number of floating point operations even further, because then you could think of this, if you look at the expression which you have for df of x, we can actually rewrite df of x in a smart way as x of 1 plus b divided by f of x. And if f of x is pre-calculated, which we typically would need in many operations, then what this reduces to is 2 floating point operations in the numerator and 1 division. So we can actually reduce this to even 3 floating point operations. So this is the kind of advantage of automatic differentiation. And if you now look at automatic differentiation, this is this kind of example that is just a typical case of something which we can formalize. So what we could do now is to assume that we have a set of input variables, and we could have some set of intermediate variables, and then set up the calculation of the derivatives using simply the chain rule here. So let's take a look at that. So let's try to formalize this example. And then when we've done that, we are going to go back to the to the back propagation. So you could now assume that you have something like, assume we have x1, x2 up to x lowercase d input variables. So we are interested in calculating the derivatives with respect to given variables. By the way, let me just also remind you of one small thing. When we are dealing with a neural network, the input variables, which we are interested in, are not the variables from the input layer, because these are fixed quantities. But the input variables, the quantities which we want to vary in order to optimize the cost functions, are the weights and the biases. So that means that not this quantity, but we are going to start with taking derivatives with respect to these quantities, or as we call them, theta 1, theta 2, etc., etc. And this is actually the kind of expression which we want to evaluate till the first hidden layer. So we don't, in a back propagation algorithm in a neural network, we don't go to the input layer. The input is fixed. So that was just a small digression, just to keep in mind when we are setting up things. Oops, sorry for that. And then when we now look at this formalization here, so you could think of having these x's could now be the weights and the biases in our neural network. And these are fed into a function f, whose derivative we want to evaluate with respect to these parameters. And then we have x of d plus 1, x of d plus 2, up to some x of uppercase d, intermediate variables. So these are the intermediate variables which I defined like A, B, C, D in the previous example. And this is this xd is the final output variable. So that's the one which we are using to calculate the function f at the end. So in the example, in the previous example, what we had the following. We had x1, which is x. So in our case, d was equal to 1. Then we had x2 equal to a, x3 equal to b, and then we had x4 was equal to c, and this x of d was equal to this variable d, which was again the same as our f variable. So what you would typically do then is something like this. So you would have a for loop of I equal d plus 1 and all the way up to the final d. And then your x of i's here would simply be given by some g's, which are elementary functions, which then receive as input something which I'm going to call a p of a, which takes as an argument x of a here. So let me just specify what this is. So this g of I, they are elementary functions. Like we saw, the elementary functions could be x times x, it could be the square root, it could be the exponential. And these x, pa of xi, which we have put in here, they are the parent nodes of the variable xi in a specific graph. Are the parent nodes. Of the variable xi, which we had in that specific graph here. So if we now look at these functions here, we could have a g2, which was simply equal to x times x squared, and that defined this a. Then we had this function g3, which is the same as the exponential. Sorry, not the exponential. And that takes this one in as argument. And that gave us this variable d. And then we had g of 4, which then was defined in terms of the c, which is the same as a plus b. So these are again the parent out variables from the previous nodes. And then we had the g5 here, which was simply the square root of c, which then gave us d here. And by definition, what we had is that df, dx of d, is the same as 1, as we agreed upon, because this is now, for that specific simple example, this is the same as our output, which is equal to the function here. So when we rewrite these equations here, the reverse mode, or what we would call the back propagation, that is simply given by the following expressions. So the reverse mode. So what you saw previously here was a forward mode, and now the reverse mode is, or back propagation, back prop. It's given by a df of dx of I, which is simply a sum over all these xj's which we have, the different outputs, df dxj of dj, the dgj, sorry, of dx of I. And this x of I is the input from the parent node for this xj here. And this pa of xj, that is the set of parent nodes of xj. And we know that we have the following. If we look at this specific example we've been looking at, the fd is just equal to 1. And then we have df dc, which is equal to df dd. And then we have d of d and then dc. And this is nothing but 1 over 2 over square root of c, because this quantity is equal to 1. Then we have the next step, which is df db, and that is given by df db, and then I have a db dA, and that's given by the exponential of a, this b, and plus df dc of dc dA. And finally, we have df dx, which is equal to df d of a of dA of d of x. And at the end, what we got was that this was equal to x of 1 plus b divided by this variable d, which is the same as square root of c. So the kind of operations we would do now, if we now look at these derivatives, the derivatives here, the way we have decoded them is now in terms of these different functions which you see here. So when we step back, go backward, we start with the output. And one of the reasons why we start with the output is that the output normally just has very few variables. Like in this case, we have only one variable, but we could have many input variables. And this is something which complicates the calculations if we start in a forward mode to calculate the derivatives. Now, one thing I wanted you to look up now, if you look at the equation which we have here, this equation for the derivatives is actually formally the same type of equation which we had for the backpropagation algorithm for a neural network. So if you look at the equation which we have here, this is essentially the same type of equation where you break everything down in terms of all the partial derivatives in this specific case. So one thing I wanted to do now, in order to see the kind of similarities even better, is to look at a simple example of a backpropagation algorithm. So this is something which we're going to do after the break, and then simple neural network. And this is after the break. And then we're going to try to see how we can understand this and get an intuitive understanding. This simple neural network is also useful when you're writing your first program, because it's a very simple case to code, and you do have analytical gradients, which are very easy to analyze. So I suggest we take a small break now, and then we move over to this simple example. And then when we're done with that, we are going to study how we can set up a code for a neural network. And we will continue to discuss that next week. We're going to look at pros and cons of neural networks and pitfalls and problems which we can end up with. So next week, we are going to end the discussion of neural networks, and then we're going to move into a discussion of convolutional neural networks. So today and next week are going in a way to wrap up. We are going to use these days to wrap up our discussions of the basic feed-forward neural network. So I'm going to put the recording on. So welcome back. We are going to now look at a simple example of a neural network where we implement the backpropagation algorithm. And when we're done with that, we are then going to look at how we can write our own program for a backpropagation. So let's just make a simple example where all the quantities which we are going to deal with are scalars. So we are going to have a network where we have an input x. So this is a scalar, there's no vector here. So this is the input. And this kind of graphical representation is always very nice. Then we have a function here, which depends on x and the weights. And now we're just going to assume that these weights are scalars, so just one weight. So we have a W1, There is no bias, but only one weight. Now this feeds in to the hidden layer, like this, and it produces an output. And we're going to call this output, as we did before, we call this output for A. This feeds everything into the output layer. And there is a new weight which connects the hidden layer with the output layer. And here we have a function which takes in this A and depends on W2. That produces an output Y, as before. This feeds into the cost function C, and we are going to compare that with a target value T. So all quantities which we have put in here are scalars. These functions F and G can be thought of as the activation functions. So let's now look at the basic operations here. So this A is the output of the layer. So this is going to be given by an activation function F, and as a function of X and W1. And then we have this variable Y, which is then given by this G, which receives as input A and has this weight W2. And we can obviously rewrite this quantity as a G as a function of F, of X, of W1, and W2 here. So this is exactly as we did before. So there's nothing new here. Then we are going to do a regression problem. We're going to define a cost function, which I simplify by having this factor of a half. So I get rid of the factor of 2 when I take the derivatives. And this is given in terms of the target minus the output from the network squared. Now, setting up this kind of equations is something which can be very useful when you're going to develop your own code for a neural network here. And then the kind of quantities which we are going to need now is the derivative of W1. We want to calculate the gradient, so we would need the gradients for W1. And we are going to set up a gradient descent algorithm. So that's going to depend on the previous value from iteration K minus, and we can have a learning rate, delta. And this is again multiplied with a gradient, with the cost function, with respect to this quantity W1. And this is evaluated at W1 at iteration K. And then what we also need is the gradient and the gradient descent formula for the other quantity, this W2, which are the unknown parameters, which we want to optimize in order to find the best possible fit for the function here. W2, and W2 now is evaluated at iteration K. So this is essentially just the standard gradient descent algorithm which we plug in here. And what we're going to do now is to assume that we have a linear activation function, just to simplify life here. So we have a linear activation function in both cases. So that means that what we're going to do now is to let f of x of W1, we simply let that be given by W1 multiplied with x. So this is as if we're going to make a kind of linear approximation to the function which we want to use as an activation function. And then we are going to have now the function g of a of W2 here, which is simply going to be given by W2 times a, which again is the same. So this is our function a here. And this is the same as W2 multiplied with f of x1 of W1. So the thing which we need now is obviously the derivative of dc dW1. And if we take these expressions which we have a cost function, which obviously depends on y. So we will get a minus t minus y here. And then we need the derivative of dy dA multiplied with dA of dW1. So that's simply just an application of the chain rule. And then we are going to have the derivative with respect to W2 here. And that, if we do the algebra, since we have a linear activation function, things are pretty simple. We can just, if we now plug it in, so let's just set in these variables. So we would have a dy of dw2 here. So this is the derivative of the cost function. We'll just use the chain rule. So if you now look at the cost function, it's just given by this quantity here. So we have y is going to depend on the parameter w2, as we see from this expression. So this is our output y. So it depends on w2, but it depends also on w1. And that's why we would have this specific expression here for derivative of the cost function with respect to w1. And then we have a similar expression when we take the derivative with respect to w2. Then these two expressions, which you see here, if we now want to perform a fit and optimization, then we will simply have to plug these expressions for the derivatives into the expressions which you have here. Now, if you look at the actual expressions we get, so we would now find that this dc of w with respect to w1 is given by minus t minus y, and it is multiplied with x. It's not a multiplication sign, but it's just multiplied with x and multiplied with w2 here. And then I have a dc w2 here, which is now given by simply the following expression. That is, let me see, where did I have it? Minus t minus y times w1 times x. So these are the expressions which we would have to encode. And you see now that these are coupled equations. So when we plug this back into the calculation of the gradients and set up a gradient descent algorithm, we would actually have equations which, for W1, the gradient for W1 depends on W2, and the same for W2, which depends on W1. Now, in general, what you see, which we have here, if you look at this expression here, this would be now the first unknown parameter. So if you're thinking of a kind of a back propagation algorithm, we would typically start with the derivatives here with respect to W2. And then with the derivatives with respect to W2, we would calculate the derivatives of W1 with respect to W1. So we are not touching the input because the input is always the same. It's left fixed. So the first term which we would need would be to calculate the derivative with respect to W1. So this is the equation which we would get. And if we now think of us having many more such terms, what we would have then would be that the dc with respect to a given w would be given now by the derivative of the cost function as we defined earlier. And then I would have now the derivatives of the function. We would have a d of y, and then I would have a d of a, and this would be the a at the final layer, and I would have dA of L. If I now propagate backward, the L minus 1, and this would continue all the way till I have a d of A2, d of A1, multiplied with d of A1. If this is now the first derivative, then we would simply have this as a chain of operations where we would end up with this equation here. So this is the essentially the back propagation algorithm. And if you look at this set of operations, this can actually be rewritten in terms of what we saw up here, in terms of this specific algorithm, which you see here, which is the same as the reverse mode in automatic differentiation. So the back propagation algorithm is the same as the reverse mode in automatic differentiation. So one thing which I will leave as an exercise for you guys, if you want to practice a little bit, you could try to link this simple model here to automatic differentiation in the reverse mode and just see if you agree with my equations. So automatic differentiation and the back propagation algorithm are algorithms which are intimately linked together here. And it's something which is not really appreciated in the community. So when you're developing a neural network, one of the things which I am very fond of when you're developing something is to take a simple model as your starting point. And a simple model for neural network could actually be this simple model which we looked at here, where we have a linear activation function here and a linear activation function here, and we have only two parameters, W1 and W2. And there we can actually almost follow by hand the way these parameters developed. And that's a very useful thing to do when you're setting up your first code. But now what I wanted to do is to show you how we can develop, based on the backpropagation algorithm, how we can develop a code for a neural network. So let's switch back to the slides. If you have any questions, feel free to do so. Just interrupt me or just unmute yourself and ask if you have questions. But now I'm going to go back to the slides, and in the slides which you have, there is a example for a neural network code, but I wanted to discuss a slightly different example. So one of the things you can do if you want to is to use now automatic differentiation. In the slides, in the regular slides, I don't use automatic differentiation. I'm going to send you this example here, but this example encodes the many different aspects which you will need when you're setting up your own neural network code. So one of the things you would have to set up, if we just skip this, it can be convenient to define the different gradient methods, because you're going to use these and test the stability of the results as a function of different methods. So we have discussed in project 1 adaptive gradient descent. This is the ADAGRAD method. So it's convenient to set up a class of functions which do these things for you. You can do adaptive gradient with momentum. You can have root mean square propagation. So these are actually quantities which you need in the setup of a neural network. And you will see that when you use popular libraries like, let's say, TensorFlow or PyTorch, these things are already included for us. So here we have examples where we have the root mean square propagation. We also have the Adam algorithm, etc., etc. So you would typically then use these. You can use momentum to adapt or gradient descent with momentum, as we discussed before the break. And you would then specify an initial learning rate, and you would have the parameter for this momentum. You can use the Adam scheduler, where you have the initial learning rate, and then you would specify the other parameters. And you would need to specify the number of epochs, and then also the number of batches which you're dealing with. So these are examples of things which you can transfer from the first project into the next project where you're setting up a code for neural network. I actually want you guys to write your own feed-forward neural network, because the basic machinery here is something which is used again and again in all deep learning models. So the other thing which you can think of when you're now setting up the code is something like cost functions. So you would then specify different types of cost functions. You could now have a cost function which is given by the root mean, the mean squared error, which is this one. You could now take the so-called cross entropy function, which is used in, let's say, logistic regression. You can have a log reg function, you have a cross entropy, and you can add many, many different other types of cost functions. And I would recommend here that you use AutoGrad, which is a very useful package, and because that allows you to calculate the derivatives easily. And then you need the next class of things, which is the activation functions. So you can identify different types. You can have a softmax, you can have a ReLU, the leaky ReLU. You can take the derivatives of these functions. You can add more functions. You have a standard sigmoid. you can add a tanh, etc., etc. So these are things which you need to think about when you're setting up your first neural network. Now, the codes which I have in the slides, on the other hand, they just go straight ahead with one of these functions. So let me just, before we look at the code which is in the lecture slides, let's take a quick look back again at the basic structure of a neural network here. So the things when you are developing a code now, what you would need is the following. So let's put up these basic ingredients. For an NN code. So when I say a neural network code, I'm now thinking of a standard feed-forward neural network where the matrices we are dealing with are dense matrices, and we perform affine transformations where we simply perform now matrix vector multiplications continuously. So we need to set up the architecture. Which then is something which translates into a model. So we would need to have the number of layers which we want to have. We need to figure out how many nodes or neurons we want to have in every layer. Then the other thing we need to specify is the type of activation functions. And from the examples, and I'm going to send you this Jupyter notebook, which I have here, because I haven't included that one in the regular lectures. And you can take a look at that, because these are things which you need to, which you can actually rewrite in terms of some specific classes, and then you can code them once and for all. So that means that you have the activation functions and obviously their derivatives, because you will need the derivatives when you set up the backpropagation algorithm. And their derivatives. So these are things which now define what I will call the model. Then the other thing are quantities like regularization, the optimization part itself, regularization, and optimization, as we discussed last time. And in here, you need then to define the type, oh, I forgot one thing here. So you need to define the cost function as well, which you want to use. And it's useful to have a given class of cost functions, which you then would simply set up once and for all, and that receives just its inputs. So you can do regularization optimization. So here you can have different hyperparameters, regularization term. So you can have a regularization parameter, this parameter lambda with either an L1 or L2 regularization. So these are the kind of standard regularization terms. And then we have the whole family of gradient methods. And these are also methods which now, based on what you did in project 1, you can reuse into project 2 here. So we need the whole family of gradient descent methods. And with that, I also mean stochastic gradient descent. So you have GD, so GD for gradient descent. So GD with momentum, which is a standard way to speed up the gradient descent. You can do stochastic gradient descent, which we normally rewrite as an SGD, with and without momentum, with and without momentum. These are just methods to speed up the iterative process. Then we haven't touched upon the learning rate. So we would then have the learning rate as parameters, learning rates. We also have epochs and batches, etc., as you have seen in project number 1. So we have learning rates, and you can have just a linear updater, You can have a exponential updater or scheduler, as we've been calling them. But normally people would use ADA-grad or root mean square propagation, which we discussed before the break, and ADAM, which is adaptive learning rate with momentum. So these are some of the most common methods. So when you are setting up the code now, try to think of how to structure it in terms of things which are unique to the specific network and defines your model, and at the same time, methods for optimizing the cost function. So you need to have a cost function. You should have a set of activation functions which you can play around with, because you don't know a priori which activation function is going to do the best job. And many practitioners, when they do neural network or deep learning calculations, they will typically play around with different types of learning of activation functions. They would play around with different architectures in terms of layers and number of nodes. And typically, if you're doing a regression problem, the cost function is pretty well defined. And the most standard one is the mean squared error. But you can do mixes of mean squared error and relative error that gives you something which is called the Huber, H-U-B-E-R, not Uber, but Huber activation function. And then we have the regularization and optimization, which becomes part of the what you might call the standard techniques to optimize the cost function. And there you would have things like gradient descent, stochastic gradient descent, and all these methods. So let's go back to the slides. And I want you actually to, the reason why I mention this now, because I want you to think about these things, because they become important when we are setting up a code for a neural network. So let's go back to the lecture slide. So things you need to define and where it's useful to set up classes could be different types of activation functions, or just simply define them like here. It's useful to use automatic differentiation. You would need to set up different types of schedulers by which way you update the learning rate. So these are functions which are useful just to have encoded once and for all. And I normally recommend, in particular, to look at the functions where you set up types of activation functions. You can make classes. You can find the different ways to update the learning rates, and also have cost functions and their derivatives, because then you can then focus more on just calling these functions and then playing around with the structure of the neural network. So let's take a look at the codes which you find in the lecture notes. So in the lecture notes, what we have done there is to look at a classification case. And the classification case is a classification case where so let me just bring this up here. So we need to encode the backpropagation algorithm. And I will show you how you can do this in a simple way without thinking of any complicated types of programming here. So we are going to look at a classification problem. And the example which is in the slide is about this MNIST data set. And this MNIST data set is a data set which contains 10 handwritten numbers. And that means that the output function is going to be given by a so-called softmax function. So in here, you will find details where we look at both a binary problem, where you can simply use the standard sigmoid function for output y equals 0 and y equal to 1. So this could be true and this false, or vice versa. You can change it to -1, +1, but it's always a binary case. So you need then to define the cost function. So in this particular case, if you use that function, the cost function is the cross entropy. And in this specific case, the y's which you have here are actually the targets which are looking after. So the output from your code. Now the numbers, the handwritten numbers, are often encoded, since you have more information than just the 0, 1, or -1 and +1. You would typically encode this in terms of a set of words, a bit string. And number 5, if you now think of you having 10 numbers, you would have 10 slots. So 0 here means that there is nothing in for number 0, nothing for number 1. And number 5 would then be the 6th one here. So you would typically encode this in terms of a bit string of a specific length. And in this specific case, 10 is the number of classes which you have in the MNIST data set. And the typical function which is normally used then is the so-called softmax function. And for those of you who have taken a course in, let's say, thermal physics or statistical physics, this is nothing but an adaptation of the standard Boltzmann function, which was used by Boltzmann to explain black body radiation. So the likelihood for this one is then simply the product of all the data points you have multiplied with the classes which you have. And you can again take the log of this function and do the optimization. And then you would find the cost function here. So in the slides, I just put in the binary case, but it's pretty easy to also look at the case when you have more than just 2 classes. So these are quantities which we discussed previously. What I give you here, because in the lectures, I used a regression type of problem. But here I replaced the regression type of problem with the mean squared error. I replaced that one now with the so-called cross entropy. So these T's are the targets which we want to reproduce, and these A's are actually the outputs Y, which we have used before. And what you will find here are technicalities with the derivatives, etc., which you would need to set up for the softmax function. But once you have decided on a specific type of function, what you will have then is the types of derivatives which you need to encode, because the backpropagation algorithm will depend on the derivative of the activation function, and clearly also on the derivative of the cost function. So when you develop a code for doing neural networks with the backpropagation algorithm, there are several things you need to think of. So one is to collect and pre-process the data. You need to actually set up the data which you want to feed in. And we are going to discuss a little bit here how you can do that. This MNIST data set makes life easy because scikit-learn actually has this MNIST data set included, and it transforms it already for you. So we don't need to think in this specific case. But actually, the kind of thinking with you transforming the data set can sometimes take 80–90% of the time, because the data which you may have may not be structured properly. We had a master student who wasted something like 1 to 2 months before we realized that the data had been taken. These were meteorological data, and they had been taken over several years. And what happened then, that in some cases, things were velocities, wind velocities were measured in kilometer per hour. And other data sets, the wind velocity was measured as meters per second. And we didn't realize that before a long, long time. And that caused a lot of problems in the training of a neural network. So things like that are things which can be painful. In this specific case, the data is already collected and you can pre-process it and just use scikit-learn. So that just feeds the data into your neural network code. And you need to define the model and the architecture as we discussed. And in doing that, you need to define cost function. You need also to define the optimizers. Then we train the model. Then you have to evaluate the performance on test data. And then you also need to adjust hyperparameters. So this is very much a kind of back and forth process here. So if you look at this MNIST data, this is a data set which actually has something like 70,000 images. Now, the data set which you find in scikit-learn has been reduced considerably by performing singular value decomposition. So the data, the images are pretty blurry, and sometimes you really have to use imagination to see that this is number 1 or number 2 or whatever. So the original data has something like 28 × 28 pixels. And there are 70,000 images. This data set which we are using here, and there's a simple reason for that, because else my code would not finish within the time of this lecture here. So this is a kind of, how to say, a vanilla version of the full data set. And this is scaled down, so you have roughly 1,800 images, and these are scaled down to 8 × 8 pixels. So the data which we feed in are going to be, so the X values, you're going to have 8 × 8 input variables, 64 pixels. So you would typically then take these pixels and transform them into a vector. That means you flatten it out. So you transform a matrix of pixels in terms of just a vector. That means that you lose this kind of dimensionality perception here. You have the 1,800 images. So that means that you have the design matrix now would contain the inputs, which are these 1,800. And then you would have the features, which are the pixels. So a typical design matrix here would be of dimensionality 1,800 × 64. And you can typically see another type. A simpler case is if you're looking at the body mass index, then you would have height and weight. And then you would have the first feature, first column is the height, and the second feature is the weight of the person. And the targets then, by using the formula for the body mass index, would simply be given by this. And then you could train a model where you just feed in the height and the weight, and hopefully that model will give you then the correct body mass index. So the first thing which you see here is actually taking the data sets from scikit-learn, which is given by this object here. And then you will simply download it, and it's just low digits. And in this specific case, what I'm doing now is simply to set up the dimensionalities. So if I run it, this specific here, you can see some selected outputs. So your inputs are now given by 1,800 images, 8 × 8 pixels, and you transform this into your design matrix, and you have a design matrix which has 1,800 × 64 dimensionality. If you were to use the full data set, you would have 70,000 × 28 × 28. So that would be a much larger matrix. And if you now connect this with a given number of nodes, that tells you how many weights and biases you would have to train. And you see these numbers have been really, I mean, they're pretty, I would say pretty blurred images. And you have to use almost your imagination here to actually guess whether these are numbers, which numbers they are. So the human success or training rate on these kind of numbers is roughly 98%. And the neural network which we are going to develop is going to give a slightly better performance than a human. Then we need to decide how much we want to have as train and test. We can also have a validation data set, but in this case, we don't have so much data. And there's a tendency then to actually skip the validation set, where you find the optimal parameter, hyperparameters. So here we will simply split in train and test. And here again, I use this functionality of scikit-learn. You could write your own function if you want to. So this will be my own equivalent function. But normally I tend to end up using the functions which are given by scikit-learn here. So if we run that one, then you can see now that we have split the data in terms of roughly 1,400 images for training, and then we have something less than 400 for testing. So the test data are data which you can think being placed in a vault, and they are not touched until you have trained the model, and then you can apply the model to the data which was not included in the training. So when you define the architecture, you have to define, as I said, the cost function. You have to define, so I'm just going to skip through this because we've been discussing this again and again. So you need to discuss the input, how big they are. So every image has 64 pixels of features. So we have an input layer of 64 neurons for each image. Then we have a hidden layer. And we can use, in this model, I'm going to use just one hidden layer, just to show you how you can build up the code. We have 50 neurons. That means that when we look at this, we have 64 input variables and 50 neurons. So that gives us the connection between the input layer and the hidden layer. So we would have something like 3,200 weights to be trained. The output then is a MNIST, is the MNIST data set. So we would have, yeah, tell me.
The number of 50 neurons in the hidden layer is an assumption, or are you following some rule?
No, this is just when you, and this is the thing which may stress you guys, is that these are parameters which you need to play around with. So when I said that when you decide upon the architecture, you will play around typically with a number of neurons, given number of neurons in each hidden layer. You can have different ones in different hidden layers. But what you should think of all the time, if you're familiar with this concept of Occam's razor, you should try to find the simplest possible model which explains your data. So if you're happy with the simplest possible model, and if that simplest possible model is one hidden layer with 50 neurons, and that does a good job, then there is no point in making a more complicated model. So this 50 is just a parameter. And what people typically would do when they do train a neural network on some specific data is to start with just one hidden layer and some few hidden nodes. So 50 is just a number, nothing more than that. So you could try different hidden layers. You can try different number of neurons in each hidden layer. So just keep in mind, these become parameters. However, your output layer is fixed, because in this case, we have 10 categories. And then it's natural to have 10 neurons in the output layer, because you're going to output 10 possible numbers. And the type of activation function which you would use then in the output layer would then be the softmax function, which is a probability. So the whole thing now is that you can use different activation functions in the hidden layer, and you can have different activation functions in the output layer. You can, if you have more than one hidden layer, you can actually start using different activation functions. But people normally tend to just use one, because else that just it just becomes at a certain point you just lose sight of what is going on, and you don't see the wood for the trees. So then we need to have the weights and the biases and everything. So the typical initialization now is to define the number of inputs and number of features, which is given by the shape of your matrix. I specify the number of hidden neurons and the number of categories, which then defines the number of output nodes, since I have 10 categories here. And then I'm setting up the hidden weights, a matrix, which are initialized with random numbers using a normal distribution. So this is just given by the number of features and the number of hidden neurons. So if I have 64 pixels, this is 64, and I have 50 neurons, so the matrix of weights is 64 times 50. So you have 3,200 weights. Then we have the bias, and in this case, you can initialize them to 0 plus a given small number. So this bias is normally set to a small number in order to avoid that the training actually stops. So in case your weights are 0, then the training would just stop, and you would just propagate zeros. So, and then we have the weights and the biases in the output layer, and we do the same here. So this is the initialization of the network. So we're just building the network here. And then the first pass now is the feed forward pass. So if we look at the feed forward pass, we are now producing an input to every node in the hidden layer. We produce an output through the activation function. And finally, in this uppercase L here, which is the outer output layer, we now produce an output which is given by this softmax function. So we have to perform this matrix and matrix vector multiplications. We will then find the input to the activation functions. And then when we have these, we have the inputs to the activation function in the output layer, which is then given by the softmax function, which then has a given number of inputs, which follows the number of nodes in the hidden layer, and then finally the number of categories. So if we then look at the feed-forward pass, what we would have then is the sigmoid function for the hidden layer. And then we have a feed-forward pass. We are setting up the inputs to the sigmoid function by setting up the matrix multiplication between the feature matrix and the weight matrix. We add the biases, and then we have the inputs to the activation function. So that produces an output. Then this output, which we have here, is then fed into the output layer. So we have an input there, and then we have the weights, which connect the hidden layer and the output layer. We have the output bias, and then we simply calculate the probabilities by the softmax function. This is the way I have coded the softmax function here. And that returns these probabilities. And then I can make my prediction. So if I run it through only once, you can see now that it makes a prediction for this image 0. So this is just one of the predictions I'm putting out. And it gives me now number 8, whereas the correct label was number 6. So it didn't do a pretty good job. And this is where we now need to go back, set up the cost function, calculate the derivatives of that, and implement the backpropagation algorithm. So next week, we are going to look at the details of the backpropagation algorithm. But feel free to take a look at the slides for this week, because that contains a basic description of the setup of a neural network code. And then next week, we're going to continue with this. We are going to dissect many of the things we have. And also, we are going to look at a slightly more intelligent way by which we can encode a neural network. So I'm going to stop here now.